Hi, my name is Jack Livingston, and this is my final project video for the Modern Biomedical Technologies class at the University of South Florida. The final result of my project was the creation of a novel use of 3D printing to assist in the cannulation of pulmonary arteries. This first image is the final model, which shows a wire entering the heart through the inferior vena cava, going anteriorly through the tricuspid valve, and finally moving up into the right ventricle and then the right ventricular outflow tract to the pulmonary arteries. The inspiration for this project came from our class discussions about 3D printing, as well as from this video tweet I saw published by a cardiologist, Dr. Sundaram, which actually got about 8,000 views and generated a lot of good discussion on Twitter. His lab is printing patients' left atria before procedures and was interested in clinical applications and research ideas. There was a lot of discussion and great ideas, and so I started thinking about it, and in the beginning stages of my project, I wanted to see if I could replicate their results. So I bought a relatively inexpensive 3D printer called the Ender 3 that requires some assembly, and I found a CT image to use. The free software ITK Snap can be used to segment the CT and generate the 3D model. Basically, you change the contrast to delineate the structure you want, and then add bubbles that will then grow to fill that structure. This is what the STL file ended up looking like for a left atrium. Once I had the file, I tried to print it with not so great results. I had to adjust the level of the 3D printer bed, as well as tweak the actual speed and temperature settings of the printer. To figure out the level, I printed this block llama because it has a square shape, which makes it easier to tell if the printer nozzle is drifting and if it's printing correctly. And this is what it looks like working correctly at the end of the left atrium print. So after I knew I could 3D print heart anatomy like the cardiologist lab was able to, I did some research and found that a Dr. Glenn Hoots at Tampa General Hospital is using a catheter system called the FlowTriever to remove pulmonary embolisms trapped in the pulmonary arteries. Here you can see a before and after picture of contrast injection, where you can see blood able to once again perfuse the lung, as well as the amount of clot that was removed that was blocking the blood flow. It's important to mention that according to the FDA, fluoroscopy can result in relatively high radiation doses, especially for complex interventional procedures such as placing stents or other devices inside the body. Risks include radiation burns as well as cancers later in life. Here is a video of the technology they are using, the FlowTriever by Inari.
The Inari Medical FlowTriever is the first and only mechanical thrombectomy system indicated for treatment of pulmonary embolism, uniquely designed to engage, disrupt, and extract venous clot. The Triever 20 features a highly trackable, large lumen catheter and large bore syringe designed to rapidly extract large volumes of clot while limiting blood loss. The FlowTriever catheter features 3 self-expanding nitinol mesh discs in 4 varying sizes that are designed to engage, disrupt, and deliver clot to the Triever 20 for extraction. Upon gaining ultrasound-guided venous access, a guide wire is advanced past the target clot in the pulmonary artery. With the dilator in place, the Triever 20 is advanced over the wire until it reaches the target clot. The dilator is removed, and with the flush port stopcock closed, the syringe is pulled back and locked into place. Opening the stopcock releases the vacuum and creates a high-flow, volume-capped aspiration, minimizing blood loss, while drawing clot through a continuous lumen into the syringe. If clot remains, the appropriately sized FlowTriever catheter is then introduced. As the catheter is retracted, the nitinol discs self-expand, engaging the clot from within. Retraction of the atraumatic discs liberates clot from the vessel walls as it is delivered back into the Triever 20. The Inari Medical Flow Triever system is designed for the removal of significant clot burden without the need for thrombolytics or consequent ICU stay.
I wanted to make this model to help with access to the pulmonary arteries for technology like the flow triever for a couple reasons. First of all, every person has slightly different anatomy, so it can help a physician plan and be prepared for anomalies by seeing before a procedure starts what he or she will be dealing with. Accordingly, because of different sizes of organs, technologies like flow triever come in multiple different sizes. Having a 3D model ahead of the procedure can help with planning and reduce cost by helping to reduce opening multiple sizes of flow trievers. Secondly, the pulmonary arteries can be very difficult to cannulate from a femoral vein access because the physician has to steer the catheter from the groin into the right atrium, across the valve into the right ventricle, across another valve up into the pulmonary arteries. This difficulty is important for safety reasons, as well as because the imaging a physician uses to do that steering is called fluoroscopy. This image, taken from a medical journal called Europace, shows some doses of radiation in millisieverts. It notes that every year, people tend to get about 2.4 millisievert exposure from normal life, such as sunlight radiation. It also notes, for example, that 50 chest x-rays are about a total of 1 millisievert of exposure. This next table, from an article published in the Radiology Society of North America, demonstrates the real exposure risks of fluoroscopy. Note that for diagnostic energies, there's a conversion here that 1 milligray is equal to 1 millisievert. This information indicates that if a physician spends even 5 minutes using normal fluoroscopy to steer the flow triever into the pulmonary arteries, that could be equivalent to 50 to 250 millisieverts of exposure, or an equivalent to 2,500 to 12,500 chest x-rays. So if the 3D model could help cut down on that exposure at all, it could be very beneficial to a patient. Using the same method as I demonstrated before with the left atrium, I was able to use ITK Snap to generate a 3D model of the right side of the heart, which is the pathway to the pulmonary arteries. I also used another free software called Mesh Mixer to hollow out the structure so that a wire can be run through the model for planning purposes. And here is some of the printing and final image again. Thanks for listening.